Hello, in this video we're going to look at the similarities between consumer and production theory. So in consumer theory there's this notion of a utility function that shows the level of utility from different market bundles of good X and good Y. A common utility function used is a Cobb-Douglas utility function of this general form where the exponents A is greater than 0 and the exponent B here is greater than 0. So here's an example of a Cobb-Douglas utility function. The exponents do not need to sum to 1. Okay, that's a common misunderstanding. The main thing for a Cobb-Douglas utility function is that just the exponents here, each one is greater than 0. And then for the production theory, there is a production function that shows a level of output associated with an input mix of units of labor and units of capital. And there's also this notion of a Cobb-Douglas production function. Takes on a very similar form here, where again the exponent here A is greater than 0 and the exponent B is greater than 0. And here's a particular Cobb-Douglas production function. Once again, the exponents do not need to sum to 1. And staying with the production side here, on the production side there's this idea of marginal products. So this is just a change in output from using one more unit of an input. We can have the marginal product of labor, the change in output from hiring one more worker, and it's nothing more than the partial derivative of the production function with respect to labor. So anything marginal in economics is a derivative concept or a partial derivative concept. And then we have the marginal product of capital, which shows the increase in output from utilizing one more unit of capital. And once again, it is a derivative concept. We're going to take the partial derivative of the production function with respect to capital, and we get the following result. On the consumer side, we have marginal utilities, the change in utility from consuming one more unit of a good. You can have the marginal utility of good X, the change in utility from consuming one more unit of good X. It is a derivative concept. We'll take the partial derivative of the utility function with respect to X. And remember, when we're taking partial derivatives, we're holding the other variable constant. That's the ceteris paribus idea, or all else being equal idea in economics. So here's the marginal utility of good X. And then the marginal utility of good Y is the change in utility from consuming one more unit of good Y, holding X constant. And we can see it as a partial derivative concept here as well. Okay, moving on. With the consumer, there's this idea of the marginal rate of substitution. In terms of a formula, it's the marginal utility of good X divided by the marginal utility of good Y. And the way I like to remember this is that the thing that we're measuring on the x-axis, the marginal utility of the thing that we're measuring on the x or horizontal axis, that goes in the numerator, and then the thing that we're measuring on the y-axis goes in the denominator. And we have this concept of the marginal rate of technical substitution on the production side. Again, very similar. We got one marginal thing divided by another marginal thing. We got the marginal product of labor. Again, it's the thing measured on the horizontal axis divided by the thing measured on the vertical axis. So usually we put labor on the horizontal axis and capital on the vertical axis. In terms of a definition, the number of units of good Y that can be replaced by one unit of good X, holding utility constant. And the marginal rate of technical substitution, a very similar definition, the number of units of capital that can be replaced by one unit of labor, holding the quantity of output constant. The marginal rate of substitution is the absolute value of the slope of the indifference curve. As indifference curves slope downwards, so they're negative, but the absolute value of that is the marginal rate of substitution. And likewise, the absolute value of the slope of the isoquant, which is generally downward sloping, is going to be the marginal rate of technical substitution. All right, moving on. In the consumer part, we have an indifference curve, a curve showing all combinations of units of good X and good Y that give a consumer an equal amount of utility. We have the notion of a budget constraint, an equation or curve showing all combinations of good X and good Y that a consumer can afford to purchase, given that consumer's limited income. And the equation for the budget constraint, we have M on the left-hand side, money income, equals the price of good X times units of good X plus the price of good Y times units of good Y. We could solve this for Y because generally if you would, this would be more convenient if you're going to graph the budget constraint here. So we put good y on the vertical axis, so we solve this for good y, and you get the following equation. The vertical intercept, the maximum amount of good y that a consumer can afford, is going to be m divided by the price of good y. We can see that the slope of this equation is negative, and it equals the price of good x divided by the price of good y. So that's the slope. Very similar things going on the production side. We have an isoquant, a curve showing all combinations of units of capital and labor that a firm can use to produce a given amount of output. And then there's this isocost line. It's an equation or curve showing all combinations of capital and labor that a firm can purchase at a specific cost. And the cost equation here is total cost equals W times L, so the wage times units of labor, plus the price of capital times units of capital. And if you're going to solve this for K to make it easier for graphing, you get the following equation. Here again, the slope is negative, and it equals the wage divided by the price of capital. All right, moving on. With the consumer, we have a constrained optimization problem. The consumer is trying to maximize utility subject to the consumer's budget constraint, given as follows. In terms of production, we also have constrained optimization, a cost minimization problem, trying to minimize the cost of production subject to an output constraint. So trying to maximize utility subject to a budget constraint, or trying to minimize the cost of producing a given level of output. So this is sometimes similar to what we're going to see here in a second, like the consumer's dual problem, known as the consumer's dual problem. So with the consumer, in terms of constrained optimization, we could think of the consumer's dual as an expender minimization problem, trying to minimize expenditures subject to a given level of utility. So trying to minimize expenditure subject to a given level of utility. And for production, in terms of constrained optimization, we could think of a production dual is an output maximization problem, trying to maximize output subject to a given cost, a cost constraint. Can't spend more than X dollars producing our product. In terms of the optimizing condition for the consumer will allocate his or her income in such a manner where the marginal utility per dollar is equal across both goods or all goods. We could rearrange this equation to get something like this. Ratio of the marginal utilities equals the ratio of the prices. And notice the left-hand side is just a marginal rate of substitution. All of these things are equivalent to the fact that when the consumer is maximizing utility, subject to a budget constraint, the indifference curve will be just tangent to the budget constraint, or will have a slope, the indifference curve will have a slope that equals the slope of the budget constraint. For production, optimization requires the following. Again, very similar looking conditions. The firm will spend money on inputs such that the marginal product per dollar spent on each input is identical. We could rearrange this equation to get the ratio of the marginal products equal to the ratio of the input prices. And the left-hand side is nothing more than the marginal rate of technical substitution. And all this suggests is that when the firm is optimizing, subject to the constraint, the isoquant is just tangent to the isocost line, or the slope of the isoquant is equal to the slope of the isocost line. Okay, that's it. I hope you found this video helpful.